All right, then. Okay. So let's begin our journey into steam. All right. So we are finally going to be utilizing that thing they made you remember all the way back in INDOC, the basic main steam water cycle. All right. We start off with our boiler, go to our superheater. We break off from our superheater. We go to our auxiliary steam, our TG steam, and our main steam. From there, we end up in our high pressure turbine. We directly go into our low pressure turbine from there. And by the way, these slides will be posted after class today. Okay. Our low pressure turbine is going to go right into our main condenser, from our main condenser into our main condensate pump. Then we go to our air ejector to our first stage heater. From there to our DC heater. From the DC heater down to our main feed pump. From there to our economizer and back into the boiler. That is our basic steam water cycle. All right. Now, we are basically breaking these things up into 4 different sections. We have our generating of steam. We have our utilization of steam. We have our condensate, and then we have our feed water side. But what is the point? If I split this in half like that, what's this point of this lower half? Why even have it?
Reheating the water so it's more efficient.
Exactly. But what else are we, since we're reheating the water, what else are we doing with the efficiency? Why bother reheating? Why don't we just take it and dump it overboard from after the low pressure turbine?
So we don't have to make more condensate.
Exactly. Think how much energy that we put into just making condensate, making distillate. All right. Now, the other thing I want to point out here as well, our steam that's coming out of our superheater, this area right here, they break off and they become our main steam, our TG steam, and our auxiliary steam. It all comes from the same line. Okay. Now, let's clear this slide. Let's continue on. So from our boiler, halfway in our boiler to our main condenser, halfway in the condenser, is vapor. The other side is all liquid. All right. Now, take a look at these pressures. All right. We are creating 600-pound steam. But look what's happening on the other side of our high pressure and low pressure turbine. It goes into our main condenser, and we are at a near perfect vacuum. So not only are we pushing and utilizing a high pressure steam, but we are also creating a vacuum and sucking through the steam through the cycle. All right. Both our high pressure turbine and our low pressure turbine are actually what's producing the force and spinning the shaft of the ship. All right. We are utilizing the main condenser and this almost perfect vacuum to suck this steam through, to create even more of a pressure differential between the two. Now, as we continue through and take a look at our temperatures that we're utilizing here. And the biggest one I want you to pay attention to is this one right here. And come on, this one right here. What's happening from those points?
It's going through the
Superheated.
superheater.
It's going through the superheater. All right. So what's happening in the superheater?
All the moisture is being pulled out of the steam.
Well, we're not really pulling the moisture out in our superheater. All right. We are pulling out the moisture in our boiler. We actually have like a little baffle before it even enters the superheater. But what is actually happening? Take a look at the temperature difference. We are removing what? We are going from what stage to what stage? All right, if we look here, we have normal pressure, atmospheric pressure. All right, so that means we have 32 degrees Fahrenheit. We have liquid melting and or freezing. And up at 212, we have liquid becoming a gas. What happens from this point on the scale to this point? What happens from point 1 to point 2?
It goes from a gas-liquid mixture to just a full gas, or just completely gas.
Exactly. What else is happening? What happens with our temperature? Remember, as we increase on this scale, we are increasing in temperature. So what else happens from point 1 to point 2? We move from a liquid gaseous mixture to just gas.
Go past its boiling point, or
We go past its boiling point, and we can only do that when? When can we only increase temperature? What is the point? What happens at this singular point when we start to make the turn and go up?
It goes from latent heat to sensible heat.
It does, but what else is happening?
All the liquids evaporate into steam.
Exactly. All right. We no longer have any liquid present. In order to go from 1 to 2, point 1 to point 2, we need to have absolutely no liquid present in order to increase the temperature. Okay? So we are still adding energy. Remember, when we are going through here, we are still adding energy across these lines. But that energy is being transformed into change of state. It is not represented in temperature. All right, so when we go from 490 degrees Fahrenheit to 885 degrees Fahrenheit through our superheater, and we are calling it a superheater because, one, there is no liquid present. So we are increasing temperature. But why? Why would we increase temperature? What is it going into next?
To increase the pressure.
Our pressure is going to stay, it actually is going to go down
Okay.
just a little bit. We're going to go from 600 to 585. Most people will reference these as one and the same. That's still 600-pound steam line. But why increase our temperature wildly? We're almost doubling it.
When it goes through the high pressure turbine and the low pressure turbine, it loses a lot of its heat. Its heat energy is turned into energy that powers the ship.
more so of our pressure is going to be utilizing that. We're going to see that later on. But what are we concerned about? What would be a big concern?
You don't want any water in the steam because the water will mess up the turbines.
Exactly. How did you guys know that? Some high-level stuff there.
540 review.
540 review.
Yeah.
All right. They're teaching you guys some good stuff in there then. So, you cannot have water molecules present because the force and the speed that this steam is going into these high-pressure turbines will be highly damaging to the blades. Okay? They will impact those blades at such a high rate of force that you can have severe damage done to the turbine blades. All right? And what we are ensuring with these high temperatures is that we will not have any water molecules hidden in our steam. It's superheated. It's superheated through our superheater. Like I said, engineers like to label things for what they do. All right. So moving through, let's go into our generation. So this is our boiler on board the TSES. All right. A lot of the times you will see drawings done in this direction. All right. Sometimes over here you'll see it as a square box. It's basically the same thing. It's just not a different type. So we're going to go into depth freshman cruise about these things, but let's just hit a little bit about them. All right. We have air that's going to travel in on the side walls. They actually travel between. Oh, I hate it when it does that. Between the furnace and the steel. All right. It's almost preheating the air, so you don't have this wicked cool air. All right. After that, we have our fuel that's being injected through our burner tips. This boiler drawing only has 2. All right. Now, this right here, this furnace area, is the spot where the flame is. Coming out of the nozzle, which you have these nozzles that are being stuck into these burners, the flame comes out kind of like the end of a fire hose. All right. You're not going to have flames all up in everything. All right. Flames are not going to be licking these tubes over here. They're basically going to situate in this spot of the furnace. Don't kid yourself. It's going to be wicked hot over here. But the flames are basically going to stay in a cone shape through coming out of the nozzle.
Are they an oxidized flame?
What do you mean by that?
As in like it's like a hot blue flame compared to like.
Oh no, it's not gonna look like you're not gonna have like a burner tip that looks like this where it's gonna be like an inside or outside flame for like if you had like a Bunsen burner. Okay, these are gonna look they're gonna be dirty. They're gonna be like they're gonna have red. It's gonna be like a deep amber color. It almost kind of looks like the fire, like in movies where they have the fires of hell, where it's just like this deep dark flame that comes out. They do have like streaks that go through it, but they're not going to be like a singular. They're not going to look like that. So they're not going to look like a torch or anything like that. These things are going to be
okay.
Coming out in a almost like a cone. we'll get more into it on why this is happening in this direction mud cruise. And that's when we are going to deeply break down these burner tips and this whole burner assembly down here. So the furnace is basically going to be sending heat through, and as the fire burns in this area, it's going to travel through and up through the stack here. All right. Now let's talk about the drums. Up top, we have the steam drum. Down, we have the water drum. So this is the steam drum up here, and this is the water drum. All right, down over in this corner here, and you can see that tube right there, and that's called the mud drum. All right, these yellow portions are called the generating tubes. All right, these tubes right here that I'm highlighting, these tubes are not generating tubes, okay? They are sitting in between your generating tubes and your water drum, all right? They're in that area. You have generating tubes on the other side of it, all right? We're gonna go over in a second what they are, but just know that your generating tubes are on the outsides of these tubes, okay? So why do we call them generating tubes?
Is it because you have your downcomers and your risers? So all the crap goes down to your water drum, and the more heated, clean water goes up.
Okay, that's one really advanced, but for you guys, basically what's happening with them, simply put, is this is where the steam is going to be generated. All right. Now, the slides go in a different reverse of what I thought it was going to be. And then finally over here, we have what's called the water wall. And these are actually protecting the outside, and they protect the actual boiler, the outside of the boiler. All right. They don't allow the heat to escape. They are protecting it with water and everything else in that line. All right. Now, we have our heat source, and this is what I want to try and get through to you guys with this. And this is with our generating tubes. Now, they are cycling in this in this fashion. They flow in this direction because we have our heat source over here. They heat up, the water travels up, and then it cools off and it goes back down in this direction. All right, but the big thing I want to tell you guys is that your steam drum isn't fully full of steam. It has a level in it, and they want to keep it about halfway. So do we have steam from here to here? From, let's say, point 1 to point 2?
No.
No. So what has happened? Why do we call these generating tubes if we can't put a point and be like, hey, from here to here is water and here to here is steam? What's going on inside those tubes? Why call them generating tubes then?
Is it because what's rising is all heated water?
It is. But the other question is that what's stopping? It's all heated water, and there is steam in here. So what's holding this water level in this drum? Do we have like check valves in all of these sections that are only allowing flow in one direction? How can we have a water level in here being held up? Keep in mind, this isn't just 3 tubes. Look over here on this drawing here. You can see the hundreds of thousands of tubes that we have. Would we have a check valve on each one of these? What if one of them breaks? No. We're not going to.
The constant pressure that just holds it up, pretty much.
Well,
Or it's constantly like circulating.
this is where it gets very interesting with this. All right. So from here to here, you got to remember this isn't going to be like all steam. All right.
Preheat. Does it have to do with it being more condensed? Like more condensed water goes down, and then like the preheated water rises up? Because heat wants to rise, right? So all the heated water will go up, but the more condensed water will fall to the bottom. So it's just a cycle. Like condensed water will fall down, but since heat rises, all the heated water, it'll try to move up.
So that it also has to do, yes, with that and also the heat source. Remember, your heat source is over on this side of the boiler, right? This is your major heat source. But what else is happening in here is that this is where it's actually, your steam is ending up. All right, so you do have this natural flow of water where the cooler water is traveling downwards and the hotter water is traveling here because of the heat sources here. All right, so you do have this natural circulation. But like I said, from here to here is not all steam. But what is actually happening in it is, let's see if I can get this pulled up real quick. All right, so what's actually happening inside of these tubes, if you have your heat source over here, all right, and you have your water drum over here, and your steam drum up here, all right, and you have your generating tubes, so inside of these tubes, you have water molecules, and it's a liquid all in here. All right. But you also have like a mixture of steam inside. And steam, and you're going to have one molecule of water all of a sudden just go and turn into steam. All right. And steam is going to rise up rapidly through it. But that steam has higher what than the water surrounding it? What's the difference between that steam molecule and all the liquid water molecules around it?
Has more energy.
Has more energy. All right. And what happens to these steam molecules as they travel upwards? Because they want to go up, right? Steam travels upwards. And that's how we get steam in our steam drum. Are they going to travel? If we have a water molecule that down here that turns into steam, is it going to travel all the way up?
No.
What happens?
There's energy to the water around it.
Exactly. So you may have a steam molecule that turns into, you may have a water molecule that turns into steam and then turns back into water here. All right. So it will travel farther than the other water molecules around it and then turn back into water because it's given up some of its energy. And then it'll kind of fall back down into its normal state and then recycle back upwards. but it might just give enough energy off to another water molecule, and that might travel upwards. And you have this cycle of happening of water molecules turning into steam and back into water and back into steam, and all happening through this entire section. All right. Now, eventually you do have steam that comes up through the top layer here. Obviously, otherwise we wouldn't work and the system wouldn't work. We wouldn't be making boats and ships and everything else out of these systems. All right. But this is the basis of what's happening. No one really truly knows exactly where the steam is really coming from at any given moment. Because of what's happening is we do know is that we do have steam molecules that are coming up. Some of them will enter into the steam drum and they will go all the way up. Some of them might even start all the way down here, and heck, they'll go all the way through this whole entire system and be steam all the way through. Some might only last an inch. But the thing is that they all will eventually become steam and produce our steam, and all of the heated vapors and all of our flame that we have over in this section and all of the heated vapors that come through and heat up and keep everything super hot in there will eventually turn everything into steam as we go through. All right. Does that make sense to everyone? Just about? All right. So, next, we have what's called our superheater. All right. Our superheater is located in between our generating tubes. Okay. And the big thing to recognize with them is why they're there. Why are they in between our generating tubes? Why, if we want to make sure there is no steam and no water molecules inside of that superheater tube, why not just have them right on top of the flame?
We're still on the whiteboard.
Oh, you're still on the whiteboard. Thanks, guys. So, as I said, here we have our superheater. All right, our superheater is located in this area in between the generating tubes. And then where I scribbled over here, why not have the superheater right on top of the flame? We're trying to make sure we have no water molecules, no liquid molecules inside that superheater. Why not give it the best possible ability to heat up? Wouldn't that be inside those flames would be the best spot for it?
It's not as hot.
What do you mean that it's not as hot?
The heat from the flames isn't as hot as the heat from the steam around it because it's all packed together.
Well, remember, our steam isn't creating a hotter heat source around it. We're not utilizing the heated pipes of our generating tubes to heat up our superheater. We're still using this flame and all the heat source that's coming through it up through the flue. All right. So this superheater, why put them in between the generating tubes? What's the main difference between our generating tubes and our superheater?
Is it because that you want to heat up the water drum? Mainly? Because that's the separating point between steam and the liquid dropping. So the superheated makes sure that all the steam is moving from the liquid, right? So don't you want it right under the water drum?
Remember the water drum here is not connected to the superheater. All right. Your steam drum up here is the only thing that's going to be connected to it. And now, why would you want to have it in this location in between your generating tubes?
Wasn't it because the heat's going to pass over that area? Having to
gonna
go
pass-
up to the stack, right?
Exactly. It's going to pass through it anyway. But what's inside of our superheater and what's inside of our generating tubes?
Water's in the generating tubes and steam's in the superheating tubes.
Exactly. So what do we want to do? If what do you think our main goal would be to why we would want to have our superheater between generating tubes? Then have them on a direct source of our heat. It has to do with the state of the water that's in there.
Generating tubes like insulate the heat inside the superheater.
So you're insulating, you're protecting your superheater. Okay? You are trying to actively keep your superheater tubes from basically burning up. Because you're always going to have water. You're always going to have a liquid in your generating tubes. All right, so we're just protecting our superheater by doing this. Okay, guys? Does this make sense before we move on?
Yeah.
Okay, good. So we come out of our superheater, and again, we're coming directly out of our superheater, and we go to 3 main lines. All right. We have our main steam stop valve. We have our TG steam stop valve. And we have our auxiliary steam stop valve. All right. All the steam on board the vessel comes out at one spot, out of our superheated steam point. Okay. It doesn't matter where it's going. It's all the same steam. Now we have 2 more valves. We have our superheater safety valve, and we have our superheater vent valve. All right, so that is it for the generation. Let's go into where we use all that energy.
Could you go back to the left side real quick, though?
Yep.
All right, thank you.
Yep. So let's talk about turbines. All right. This is an axial flow turbine. All right. So as we go through, we have a nozzle right here. And we have turbine blades right here. This is the simplest turbine we can do. All right. So this blue line right here is representing steam velocity as we go through the nozzle and as we go through our axial flow turbine. All right. So steam velocity increases as it goes through our nozzle. It plateaus because it has not done anything. It has no restrictions. All right. And then as it goes through our turbine blade, we are losing velocity because we are putting a force onto every one of those turbine blades. That is us losing energy. All right. We are transforming it into the rotational energy of this turbine blade. Okay. So of course, we can't just create this from nothing. All right. So our steam pressure, as we are going through our pipeline, nothing has changed. As soon as we enter this nozzle, we decrease our steam pressure. All right, and it plateaus on the other side of it. And this is what's happening. We have that cross. this cross right here, as our velocity increases, our pressure is decreasing. Okay? So this is our high pressure turbine. We have a 3-stage impulse turbine. We have nozzles. All right, the nozzles are stationary. They're fixed in a nozzle diaphragm attached to the turbine casing. All right, these are all our nozzles, these purple pieces right here. All right, now we have the blades. These are the half moon sections. All right, blades move. They're fitting to a wheel and attached to the rotor shaft. Now, a singular stage consists of a set of nozzles and a set of blades. All right, so like the picture just showed, this is one stage. This is another stage. And this is the third stage. That's how we get a 3-stage impulse turbine. All right. The other thing to note is that each time we go and enter another stage, the blade wheels are increasing in size. That is done on purpose, and that is done because we are using a force. All right. Every time we go through a nozzle, we lose pressure, but we're increasing in velocity. And then when we go through a nozzle, we decrease in velocity, but we still have more energy to give. All right. So we need a bigger surface area to act the same amount of force for less velocity or less pressure. Okay? Does that make sense to everybody? If it doesn't, speak now.
Yeah.
And that's why turbine cases are always drawn like this. That's very bad drawing, but you can tell that it's one side is larger because of what's happening. We have a larger blades on one side, and why the low pressure turbine is so much bigger than our high pressure. All right. And as we see, as this arrow is representing, the steam is expanding as it goes through, and it's using more force as it goes through each stage. All right. And there's a nice spinning animation for you guys. And as we see, the nozzles do not move. It's only the blades. Now here's the big thing. The high pressure turbine is geared directly into the main shaft of the ship. All right. This is a smaller pinion gear right here. And then this is a larger gear here. So this shaft right here is not the main shaft that goes through the vessel. This is not attached to the propeller. That is not correct. Okay. Now, if we look at this, come on. Sometimes these animations are just a little slow. And we look at the arrangement on the TSES. All right, we have our high pressure turbine, and we have our low pressure turbine. All right, we have the main boilers over here. All right, and over here we have the throttle box and that whole assembly. Okay, just keep your bearing. So we have our crossover. All right, we have our head steam. It enters only through the high pressure side. And we have our stern steam. and that enters only through the low pressure side. All right. I cannot stress this enough that the astern only goes through the low pressure and the head only enters through the high pressure, but it does go through the low pressure turbine. The astern only goes through the low pressure turbine and enters only through the low pressure turbine. Okay? The head steam goes through the high pressure, through your crossover, through your low pressure turbine casing, and down into your condenser. The astern just goes through a portion of the low pressure and down into your condenser. All right? So let's look at our high pressure turbine on the TSES. We have 9 impulse stages. All right? We have what is known as a steam chest. All right, this is where all the steam is entered. And there's our crossover to the low pressure turbine. Now we have another HP bleed, or the high pressure bleed. It's in the 6th stage. So we've counted 1, 2, 3, 4, 5, and after the 6th stage. All right, that's utilized in startup. And then we have what is known as the bleed, the IP bleed crossover extraction. Again, not used in normal operations. Just know that it's there. All right. Now let's look at the low pressure casing. All right, we have 4 impulse, 1 transition, and 4 reaction. All right. That is all this side right here. This is all utilized for a head steam, okay? And only a head steam. There is no wall that separates these two. There's nothing there. What is there is our condenser sucking all this steam down right in this spot. All right? So on the astern tube side, we have 1 Curtis and 1 impulse stage. Here's our crossover from the high pressure turbine. And here's our exhaust trunk to the main condenser. And you notice that the crossover, so our head steam, is coming right through our head turbines and down into our exhaust trunk for our main condenser. And our head rotation is one direction. And we go into our stern. And our stern steam only goes through, and it's in the opposite direction rotation. We have our LP bleed. And again, just used in startup and shutdown. So how do we determine C speed? All right. That's the big question of the day. So we have our big casings, we have our crossover, and we have our steam chest. And we basically utilize something called nozzle control valves. All right, we have 4 of them, and they're only on the steam chest for the high pressure turbine casing. All right, C speed. The definition of C speed is long duration, it's port to port. All right, it's not maneuvering. Throttle is at a fixed position. It's usually wide open. All right, these nozzles are not, semi-open or semi-closed. They're all the way open or all the way closed. That's how do we utilize them. All right, we have the nozzle control valves. Opens at a chamber to a set number of first stage nozzles. And the number of nozzles open corresponds to a particular engine RPM and hence C speed. So these are particular RPMs. All right. So this is looking down at the turbine. All right. So we are taking a look at it this way. So this is where the steam enters from our high pressure from our boiler. All right. There's nozzle number 9. There's nozzle number 12. Now we can do two things. We can add. So we have nozzle 4 over here. 4 and 9 is 13. All right. And we have 1, 2, 3, 4. Same thing over here. We have 1 through 9, 12, and then 14 over here. All right. That's how many nozzles we have going into our turbine blades. And then there's 14. All right, so let's say we have a fixed number of nozzles open, and we have our head throttle. All right, where are these located? All 3 of these. The astern guardian, which is a new term for us. We have the astern throttle, and we have the head throttle. Where are those located?
Throttle box.
So there's 2 of the 3 are located on the throttle box. Which 2?
Astern and ahead.
The astern and the head what?
Throttles.
Okay, so these are on the throttle box. All right. So where's the astern guardian valve?
Is that right next to the throttle box to the left? It was like a huge one. I thought that was a Stern Guardian I saw. It's right next to it. It's like to the left, I believe.
Yeah, so when you're looking at your throttle box, all right, and you have your stern and your forward, there's a big valve right here, and that is your astern guardian valve, okay? If you're looking at this box, both the high pressure turbine would be here, and the low pressure turbine is right here, okay? You technically at this point be looking forward on the vessel. All right. So like I said, if you open up your head throttle, you're going to be getting steam going through from your boiler, through your nozzles, through your high pressure turbine casing, through your crossover, through your low pressure turbine casing, and down into your condenser. All right. Now, if we open up the head throttle more, we're going to get more steam, and we're basically going to be putting more steam through these casings. All right. Now, we close that ahead throttle, and we open up this astern throttle. The astern guardian valve is to do what? Why have one?
Doesn't it stop the astern steam going through?
Okay, what else?
So they both don't run at the same time.
Yeah, because that would be really bad if we had both the astern throttle open and the head throttle open at the exact same time. Okay, the astern guardian, just as we talked about, will go either fully open or fully closed. These astern throttles are throttled. All right, so they can get and not close all the way. All right, so you don't want steam leaking through and going into your stern when you're trying to go ahead. All right, and this is also just for protection, just in case someone opens up the astern by accident. All right. Let's watch that animation. So you open it up, you have steam going through, but it's only going through those front portion of the blades. All right, so that is our low pressure and high pressure turbines. Okay, the big thing to realize with it is that both turbines drive the ship's shaft together. All right, it's not one or the other, they work together to turn the shaft. All right. So going through, we have a shell and tube type heat exchanger. This is our condenser. All right, going through a shell and tube type heat exchanger, we have fluid 1. Fluid 1 is giving up heat. Fluid 2 absorbs heat from fluid 1. Either 1 or 2 may be the primary fluid. And then either fluid may be inside or outside the tubes, but keep in mind these aren't directly connected. They don't contact each other, all right? If you were to look down this way at the shell and tube type heat exchanger, you would see a massive amount of tubes, all right? So every one of these tubes represents a tube in this drawing, okay? Now, this on our condenser is our LP turbine right there, and this is salt water going in and then salt water overboard. And then this is our condensate. All right. So with a shell and tube type heat exchanger, there's a couple of different terms. You have a heater, so its primary fluid does not change phase. It increases in temperature only. All right, so an example of that is our fuel oil heater. You have a cooler. Its primary fluid does not change phase, but decreases in temperature. Remember, this is what we're either trying to heat or cool via some sort of fluid. All right, so this example is our lube oil cooler. Then we have an evaporator. All right, primary fluid changes from a liquid to a vapor, absorbs latent heat. And then we have a condenser, which is our primary fluid changes from a vapor to a liquid, and it's giving up its latent heat. All right. So this is the main condenser on board our vessel. We have the main circulating pump. This is salt water. All right, the salt water goes directly overboard after we're done with it. We have our steam coming in from the low pressure turbine up here. And we have our main condensate pump that is pumping our liquid that forms to the rest of the system. We have an air drag line. This goes to the air ejector. Why have an air ejector? What's the point of it?
Isn't it to put pressure back into the system?
So remember, it's doing the opposite. What we're trying to do is draw out any of the non-condensable gases. We're trying to create a vacuum. And that's what this is doing. The air ejectors are creating a vacuum. All right. So you're removing, because we want to have like a 29.5 or 28.5. We want to have a damn near perfect inches of vacuum. Because remember, 30 is a perfect vacuum, but that's unachievable. So a perfect vacuum is considered anywhere from 29.5 to 28.5 inches of mercury. All right. Now we do have a main condensate, main circulating pump, or main saltwater pump. But what also can we utilize on board the TSES? How else can we get salt water to go through our condenser? It's another way. So on board the TSES, we also have something called a scoop. And it literally is on the bottom of our vessel. And it sticks out on the bottom. And basically it just scoops up salt water from our movement and goes into our condenser. And then it spits it overboard. All right. The only mechanical portion of it is a valve. All right. And that is to stop the salt water from going through when we don't want it to. All right. Otherwise, we are utilizing a main circulating pump. So this is a non-mechanical version. All right. It's just a scoop. It literally is just grabbing water as we move through the ocean. All right. So let's talk about the main air ejector, which is the next spot that our condensate travels through. All right. So this is coming from our main condensate pump. So this is coming from our condenser to our condensate pump, and then it enters into our air ejector. So who knows where the air ejector is on board the TSES? Where is it?
Is it in the lower engine room?
It's not in the lower engine room. All right, let's see what we got here. All right, so here's a little drawing. We have our high pressure turbine. Oh, I still have the eraser on. We have our high pressure turbine. We have our throttle box. That's our stern guardian. All right, we have our alarm panel here. We have our boilers. This is aft. If that helps anybody. This is forward. All right, our TGs are over here. We have our Nyrex over here. This is our burner bench. So let's start moving down. What do we have in this spot right here? Give you guys a hint. Draw the symbol for it. What is right in that spot? There is something called a bullseye that's right here. Is that helping anybody remember what this piece of equipment is?
Strainer?
Strainer for what? So that's a duplex strainer symbol. But what's the strainer for?
The water.
Nope, this is our lube oil. All right, so that's our lube oil strainer. So if we move down, there's also something, we have a Quincy air compressor in this general vicinity. All right. Now, our air ejectors sit right here. All right. There's that big whiteboard right here. All right. We have, in this spot, we have our reefers. All right. We have what used to be two both of these spots right here used to be our distillate makers. All right. So these were our evaps. Our flash evaps we actually had. All right. And this right here is our air ejector. So let's go back to the PowerPoint. But always keep in mind when we're talking about these components where they are on board the vessel. All right. Don't just think about something that this is, it's just whatever on the PowerPoint. Because I guarantee you will affect you.
The air ejector has the relief valve on it, right?
For
I just remember like going in the engine room and next to the lube oil strainer by the air ejector there is maybe it was a safety valve. I don't know. They would tell us that that it would whistle.
okay, so there is what's called a gooseneck right here. That may be what you're thinking about, and this is just an air vent. All right. There is a safety valve over there. I'm trying to remember, but I say it would whistle or would it clatter?
They would say that like the pressure, like something would build up and it would pop.
Okay. So more than likely it was a reducing station of some sorts. I'll have to go take a look at it when I get back on board, and back on campus. But from my memory, I don't remember anything whistling right there. But what we do have is our air vacuum drag line. So this is coming from the condenser right here. All right. Again, we're still using the Venturi effect in these portions. And these are 150 PSI auxiliary steam, which is coming from our boiler. All right. It goes through a reducer station to go from 600 PSI to 150. Okay. So we have two stages. We have our first stage and our second stage. All right. And now this is our condensate going through. This is another shell and tube type heat exchanger right here. All right. So the air ejectors sit on top of it. And then we are utilizing the 150-pound steam that is getting mixed with the vacuum air drag line of the non-condensables. We're utilizing that to heat up our condensate, all right, before it goes to the first stage heater. All right, we do have portions that drain to the ADT, all right. So enter the condenser, we're at 10 to 15 inches of vacuum, and then the after condenser is about 1 atmosphere. All right, so the ADT is the atmospheric drain tank. And then we have the return to the condenser via a loop seal. So this is just sealed from our inner condenser. All right. So we got through everything that I wanted us to get through for today, and actually more. So Monday's quiz is going to be slides 1 through 24. All right. Slides 1 through 24 is Monday's quiz. All right. And again, that quiz is going to be 10 questions. Make sure you download these PowerPoints. All right. Blackboard's been really sketchy to me. I can imagine it's getting sketchy to you guys too. If it's giving trouble that you can't download these things, and as long as it's a reasonable point, and it's not 5 minutes before the class, let me know and I'll just email it to you. Does anybody have any questions before I release you guys?
What did you say the slides were again that the quiz will be up to?
1 through 24. All right, so that'll be quiz 4. So just keep doing what you guys have been doing. All right, come in, take the get ready to go into the examination folder on Blackboard. We'll take the quiz. All right, and then we'll continue with the rest of the day's lesson. All right. Other than that, if you guys have any questions, I'll stick around for a few minutes, but I don't have anything else for you guys. But have a good
day,
weekend.
Professor.
Have a good day.
Have a good one.
Professor,
What's going on?
just for the hydraulics and what will be on the test, is that the steering gear and then what we did at the next class with the sliding doors and the hydraulics of them?
Yeah, so it's going to be all hydraulics 1, 2, and 3, all the electricity, and all of what we're doing with steam.
Okay, thank you.
No problem.
Have a good day.
You as well.
I think I found it in my notebook. It releases the non-condensable gases. That makes
Okay,
sense.
so that's the gooseneck then.
Okay, all right.
All right.
Thank you. Have a good
No
day.
problem. Yep, you as well then. Anybody else need anything?
Professor, for the electricity, are we supposed to study about the electrical appliances or not? For the electricity.
Say again, I'm sorry.
The electricity, I checked through the notes and it's only electricity, or are we supposed to add electrical appliances or not?
Electrical appliances?
Yeah, because
So it's only covering what we did in electricity in class. All right.
Okay.
So the entire electricity PowerPoint.
all right.
All right. So pretty much all of the electrical from slides 1 through 36, all the electrical distribution, everything. Okay.
Okay. All right, sir.
I mean, you don't have to know exactly how a toaster works, but the idea of where the grounding wire is attached to.
Okay.
Okay. Where you can replace a toaster with a motor and know that the grounding wire is still attached physically to the casing of the motor or the casing of a toaster. Okay.
Okay. All right, sir.
All right. Hope that answers your question.
Yes, sir.
Okay, good. Anybody else have any questions before I end, or? All right. Everyone else have a good day.